Welcome back everyone. In the last class we had seen the different types of specifications that are linked to unity negative feedback configuration second order system. Today we move ahead from that point and we will try to see the effect of poles and zeros on the response of a system. Before that, a quick recap. Here are the specifications that we had talked about in the last lectures. The step response was given by this formula and the poles of the standard second order system was given by these formula, minus zeta omega n plus minus j omega n root over of 1 minus zeta square. Now today we take a simple problem. First, suppose you are given a system as given in this diagram where the transfer function is 1 by s plus 10. You have modeled the system already and you came up with this transfer function. We want that the response of this system should be such that, or the step response of this system should be such that the settling time is 0.8 seconds and the peak overshoot is 16.3%. In general, if you give a step input here, there is no guarantee that this is going to happen and you can check this on your own using simulation that this will never happen for this transfer function directly. So, we will have to do something. And what are we going to do? We are going to create a feedback path. We measure the output, we feed it back into the system and here we will give a reference input which is unit step, and by changing this value of k we will try to reach our goal. Remember, this is the original system and these are the parts which we are adding to the system, or we are creating this configuration for the system. So, how do we go ahead and solve this? So, the first thing that we will do is we will try to see what is the desired closed loop poles of this system. So, we know the standard, this is a standard unity negative feedback configuration. So, we know what the closed loop transfer function will look like. This will be the closed loop transfer function, and so now you see from here we know that the peak overshoot is 16.3%. So, from there we can find out the value of zeta. Since settling time is 0.8 seconds, we know that zeta omega n must be 5 in this case because 4 by zeta omega n is 0.8, and from there since we already know what zeta is, we can find out omega n. So, omega n comes out to be root k here, right. So, zeta omega n is this, zeta is 0.5, and so from there I can always find out what is omega n will be 10, and since here in the standard form this transfer function, so this part, this constant is nothing but omega n square, right, because the standard transfer function was omega n square divided by s square plus 2 zeta omega n s plus omega n square, right. This is what the standard transfer function look like. Okay. So, omega n square is equal to k, therefore, k must be equal to 100. So, you see, by using the simple formulas that we had derived in the last class, we can find out the value of k. Now, you feed in this value of k 100 here, then the output here would be such that it has a settling time of 0.8 and a peak overshoot of 16.3%. Great. So, this is how we can simply design a controller, where the controller here is a very simple controller, it is just a constant block, we can easily design it. Will I be always able to do that? Might not be always possible, we will look into cases when it is not possible as well, but later on. Now, what we are going to see is, okay, when you model a system, you may get it in the standard form, but there is no guarantee that the model system may be in the standard form. So, what do you mean by that? Consider this simple closed loop system, and if you find out the transfer function of this system, you will see that the transfer function of this system is 4 by s square plus s plus 12, which is not in the standard form because the numerator here is no longer equal to the constant here. So, it is not in the standard form. Does this mean that whatever we have studied till now goes in vain? No. Okay. Let us see what happens if this is not in the standard form. So, seen that the constants here are different. So, what I have done here is taken this constant to be a k and this to be omega n square. So, they are two different quantities now, and let us try to find out what is the step response of this system. Okay. So, ys will be equal to k by this transfer function multiplied by Rs. Rs is 1 by S, right, because we are giving step input. So, Rs is 1 by S. Now, here is the trick that we are going to do. So, what we are going to do is we will write it in the standard form, the transfer function, but since we are introducing omega n square, we can multiply with k by omega n square, we get back the same thing. Therefore, what will be yt then? Yt will be Laplace inverse of ys, which is nothing but the Laplace inverse of this entire quantity, which is this. But since this part is a constant, I can take it out, and then the Laplace inverse of this part is nothing but the standard Laplace inverse thing that we have already done. So, this will be the response of the system. Now, when you look at the response of the system, what can you notice? So, suppose I draw the response of the system. Okay. So, this is time, this is yt, and in the standard case this was 1 and this was the response of an underdamped response, right. This was the standard case. For this case. Now, what we are doing? The same thing, but there is a k by omega n square multiplied here, which means since there is a k by omega n square multiplied, everything here in the y axis will be multiplied by k by omega n square, right. So, this is what it will look like. The time scale does not change, right, there is no change in the time scale, which means the value of Tp, the value of Ts, the value of Tr, these remains the same, correct, they are not changing because in the time scale there is no change, only change has been in the y axis. So, the only parameter that is dependent on the y axis is Mp, and what was Mp? Mp was y max minus y steady state divided by y steady state, right. Now, in this case what is y max? This will be y max, right. So, y max will be multiplied by k by omega square, k by omega n square. Similarly, ys is what? Ys in this case is k by omega n square, and ys means the steady state error, the steady state value. The steady state value is still k by omega n square. So, what will this be then? This will become k by omega n square. The maximum value, you check what was the maximum value in the derivation that we had done. This was that maximum value for the standard case, that will get multiplied by k by omega n square. W yss will become k by omega n square divided by this becomes k by omega n square. So, you are left with again the same formula, right. So, this is all in percentage. So, this is in percentage. So, you see specification wise there has been no change, the specifications are the same even if the constants here differs. Only thing that is fixed is that the poles of the system are not changing, the poles of the system are the same. Okay. So, for in this type of case scenarios, you can actually again use the same specification. So, there will be no problems at all, the specifications remains the same. That is why that specifications has been made in such a way that it is not affected by just scaling the transfer function. Now, let us look into the case when we have additional poles in the system or additional zeros in the system. There is no guarantee that you will always get a second order system. It may be third order system, it may be a second order system with zeros in it. So, there is no guarantee of a second order system. So, let us see what happens if we add an extra pole into the system. Okay. So, what is the effect of an extra pole in the system? So, in order to see that, what we can do is that, so we are trying to find out the step response, right. So, what is the effect on the step response of the system? So, this entire expression can be written in this partial fraction form. I am not concerned about what are the values of a, b, c, d here are, because you will get something based on the values of zeta, omega and k here on alpha. So, I just want you to understand the concept here. So, you see what will be ys in this case? It will be some form of this partial fraction, right, because what is ys? Ys will be equal to this transfer function multiplied by 1 by s, right. So, then we do a partial fraction, we get something like this, and then we will do a Laplace inverse of that, and the Laplace inverse of this would come out to be something of this form. A by s will become a, this part will have some e to the power of minus zeta omega and t and this term. So, this is almost similar to the standard case. The additional thing that is coming is the effect of alpha. So, d e to the power of minus alpha t you will get. Now, you see if this term is negligible, then the effect is only dominated by these two terms, which is similar to the standard case. Standard case means the standard second order case that we had been studying till now. However, if this part is not dominant, it becomes dominant in the sense that this part has a higher value, then there will be a problem, because this will affect this part of the expression. So, this is the part which is crucial here, and we will see that this will have an effect. So, you see, if alpha is large, then the term d e to the power minus alpha t goes to 0 faster, because e to the power of minus 100 t and e to the power of minus 2 t, if you compare, e to the power of minus 100 t goes to 0 faster compared to e to the power minus 2 t. So, if the value of alpha is very high, then the effect of this term is low as t increases, right. The reason being that e to the power of alpha t, if alpha is very high, it will die down to 0 faster. So, at higher times, so the effect of this term will be very less. Now, what is the meaning of alpha being large? You see, if I do a pole 0 plot, real part and imaginary part, this system had 2 poles and this is the third pole, right. So, this is the third pole at minus alpha. So, when alpha is large, this means that this pole is further away from these 2 poles. So, the effect of these 2 poles are dominant in the system if this alpha is too far away from these 2 poles, but if this pole is nearer to these two poles, then the effect of this term will also, so this term will also dominate on the other terms. So, basically there will be, the effect cannot be neglected in that case. We can see this with the help of a simple simulation. Let us look at that simulation now. Here is a second order system TF. So, this is how you can write the transfer function also. So, this is the numerator coefficient 16 and this is the denominator s square plus 6s plus 16. So, this is a second order system, standard second order system, and we are adding a third pole which is 1 by s plus 1. So, this is like what I am writing is 1 by s plus 1 plus, did I write 6? So, I think I wrote 6. So, 16 by s square plus 6s plus 16. So, instead of taking it in this form, I have already taken it in the partial fraction form. So, this is the system say. Now, the question is, will this part affect the response due to this, because see, this part is a standard second order transfer function. Okay. So, let us see that. You see, so what I have done is cis second is the standard case, cis add is the first order transfer function. Cis I am adding these 2 transfer functions and then I am plotting step cis add and step cis. So, this additional and this one I am plotting. Let us see how does they look. So, here we have 3 plots. You see the blue one here is the second order system. The yellow one is the final, is the third order system, which is addition of the first pole to the second order system, and then we have this first order systems function. So, you can see here that this first order response is affecting the second order response quite a lot, because alpha in this case is 1. Now, what happens if I change the value of alpha to say 10? Okay. So, that means the third pole is at minus 10 now. So, you see, now you see the effect of the third pole is quite less. See, this blue line is nearer to the third order system. Now, if I keep on changing this, if I make it 100, you see what happens. Again, I will to just get rid of this. So, you see, in this case, the third order and the second order system are very nearer to each other, because the effect of this first order part is quite negligible. So, as alpha moves away from the poles of 16 by s square plus 6s plus 16, the effect of the third pole becomes negligible. Similar analysis can be done for zeros as well. So, suppose this was your system, there is an additional 0 in the system. Now, if you go ahead and write this system in again partial fraction form, this will be what it is. And notice here, this part again I can write in the standard form, where I can write k by omega n square multiplied by omega n square. So, this part is standard, okay, and again this part again I am writing in a standard form, okay. So, this is just the same thing but written in a different way. Now here what is the Laplace inverse of this? If the step response of this is this, then the Laplace inverse will give us, you see, k by omega n square. For this part, this is what, s multiplied by this, right? If you remember the Laplace of f of t, if it is fs, then the Laplace of d dt of f of t is s fs considering no initial conditions, right. So, that is what is happening. This is s times the standard form. So, therefore, this is d dt of c1 t here, okay, and this should have been y, this should have been y, okay. So, similarly, for this part it is k alpha by omega n square c1 t. So, now again look at this expression and you can make out as to when will the second order response dominate. So, for the second order response to dominate, this term should be very prominent, right. This term should not be prominent, and this term can be made prominent if the value of alpha is very high. Okay. Now, what is the value of alpha high means? If the value of alpha is high, so you see this is a system of this form, there are two poles in the system and there is a 0. Zeros are always symbolized by like in this way and poles are symbolized by crosses. So, this is a 0, suppose at minus alpha. Now, if the value of alpha is high, again the alpha has to be further away from these two second order poles, then the effect of this term will be much higher, and that is what we are going to see. So, if alpha is higher, then the second term is prominent. If alpha is comparable to the other poles, then the first summand is also prominent. We can see this with the help of a simple simulation also. Let us look at the simulation. So, here I have 4 systems, okay. So, the first one is 20 by s square plus 2s plus 2. So, let me just write it down. So, 20 by s square plus 2s plus 2 is the first system that I have taken. So, this is cis or 0th system, okay. So, let me take the other two, let us see what are the other cases. Also the denominator is s square plus 2s plus 2, but the numerator in this case is 20s plus 2, in this case is 4s plus 20, this is 20s plus 20, 4s plus 20 and 2s plus 20. So, let us write it down. So, 20s plus 20 by s square plus 2s plus 2, 4s plus 20 by s square plus 2s plus 2, and then we have 2s plus 20, that is s square plus 2s plus 2. What are the poles of the system? In this case the poles of the systems are minus 1 plus minus j, because the roots of the denominator in this case are minus 1 plus minus j. Now, look at this, what is the 0 of this system? This is at minus 1, the 0 in this case is at minus 5 and the 0 in this case is at minus 10, right. So, we have these 4 systems, and in this case you see minus 10 is further away from 10 times away from minus 1 plus minus j, this is 5 times away, and this is exactly where minus 1 plus minus j is sitting. Basically the real part is the same in this case. So, let us look at this response. You see in the response, when there is no 0, this is the blue curve, this is the standard second order case. When there is minus 1, you see the orange curve. So, see the response, because the first term in this case, this term is getting predominant in this case. For minus 5, see it is very nearer to the blue one. So, in case of minus 5 also the effect is quite negligible, at minus 10 it is almost negligible. See, as t becomes higher, the effect is almost negligible. It is only in the transient part that there are some effect of those zeros. So, what does this tell us? This tells us that you can actually go ahead and approximate a system with a second order system. What do you mean by that? Suppose you went ahead and modeled a system. You had a plant, okay, you modeled the system, you got a transfer function. It had suppose many poles and many zeros in it. You then connected it in the negative feedback configuration, say unity negative feedback configuration, and you found out the transfer function, closed loop transfer function. Now, the closed loop transfer function of the system had many poles and many zeros. Now, what you can see is that where are these pole locations located? Suppose there are 2 pole locations which are present near the imaginary axis. Now, what is near, what is far, we will also get to that. Suppose near the imaginary axis, and the other poles are further away, quite at least maybe 10 times away from these 2 poles. then the effect of these two poles which are near the imaginary axis will dominate the response of the system. In the similar way, if the zeros are also 10 times away or 5 times away from these two poles which are near the imaginary axis, the effect of these two poles will dominate the response of the system, which means I can approximate the system with a second order system, and that is what we are going to see next. So, generally the idea is, if you have a higher order system, we try to approximate the system with a second order system. Why do we want to do that? Because if we approximate the system with a second order system, then I can use all the specifications that I have talked about in the last few lectures and use them, because it is not possible for us to go through each and every order of system and analyze them. So, instead of that, we approximate the system with second order system, we analyze the system, we design our controllers for those type of systems, and then we apply the controller that we had designed in these higher order systems and see how the response is. If the response is fine, then well and good. If the response is not fine, you come back to the design table and then again reiterate and design the system from the starting point. From the starting point, what I mean by that is that from the point where you have made the first copy of the controller. So, you made a first copy of the controller, test it. Okay, it does not work or it is a bit it is nearer to what you wanted, you make changes in this first initial copy and then you keep on iterating and then finally reach to the controller that you want to design. This is what the design process is. Now, how do we approximate a system? So, for that, first you have to identify what is called dominant poles of a system. So, dominant poles are the poles which are closest to the imaginary axis. These are the poles. So, when poles or zeros are near to the imaginary axis, then their effect is dominant on the response. So, they are very important. Okay. So, the poles which are closer to the imaginary axis are the dominant poles of the system. Okay. Now, how do we approximate the system? So, first of all, higher order system with multiple poles and zeros can be approximated with second order system if the poles are 10 times away from the two dominant poles and zeros are at least 5 times away from the two dominant poles. Okay. If this is true, then you will be able to approximate the system. If not, then what? If not, also you try to approximate, but of course, the controller will not behave or the system will not behave as you wished because the formulas will not be valid then. However, you can at least get an initial guess and then work on it. Okay. Second is, while approximating a system, ensure that the final value and the original of the system are same. Now, what do we mean by that? So, for example, this is the system that you had. Here is an example. Now, 20 by s plus 10, s square plus 2s plus 20. Now, for this system, if I wanted to approximate the system, you see, for this system, where are the poles? If I do a pole 0 plot, so remember, this is the closed loop transfer function, right? I am not giving you the plant transfer function. This is the closed loop transfer function. I have already closed the system and found out the transfer function of the closed loop system, because at the end we are seeing the output from the closed loop system only, right? Not the plant only. So, it is already connected in that configuration that we had talked about. We found out the closed loop transfer function. For that closed loop transfer function, this is what we are getting. There is a third pole in the system. So, which means the pole locations are -1 plus j, -1 minus j, and the other one is a -10. So, this is the real axis, this is the imaginary axis. Okay. So, now you can see that these two poles are the nearest to the imaginary axis. So, this can act as dominant poles. So, these are the dominant poles and this third one is 10 times away from these two poles. So, I can actually get rid of this third one, right, because this third pole is at least 10 times away from the two dominant poles. So, the effect of this will be quite negligible. So, then just by looking at the transfer function, can I write that the second order approximation is this? This will be the system because I just got rid of this. Let us see whether that is true or not. For that, I will just go back to this. So, let me just write down a transfer function here. So, we know already how to write down a transfer function. There is another way of writing down the transfer function. So, S equal to TF, first you define S, okay. So, this is your S and then the transfer function is G equal to 20 by S plus 10 whole into S square plus 2S plus 2. This is the transfer function of the system, closed loop transfer function. Okay. So, if I find out and what was the approximation? So, G approx is 20 by, I just got rid of the S plus 10 term. So, this is what it is, right. So, let us see step response, step G. Okay. So, then we hold on to it. So, let me see if there was already a figure. So, let me just get rid of these. Okay. So, step G. So, this is the step response of the original second order transfer function. Let me hold on to this, and then I give step the approximated transfer function, which is APPX. So, this is what we get. So, let us see how it looks. See, this was the original one and this is the one that you had approximated. There are no way the step response is similar. Now, what is the problem here? The problem is that you see the steady state value in this case was 10, whereas the steady state value now is 1, the opposite way around. The steady state value for this one is what? 1, right. So, how do I find out the steady state value? So, I hope you guys know how to find out the steady state value. So, try to find out the steady state value on your own. I am not going to do that for you now. So, suppose this is the standard transfer function, this is the closed loop transfer function, you have to find out the steady state value. You know what is YSS? YSS is limit of S tending to 0, S of YS, right. So, this is what you have to find out, and what is YS? This transfer function multiplied by 1 by S, because we are trying to find the step response of the system. So, in this case the steady state value is 1, in this case the steady state value is 10. So, this comparison is not valid, that is the reason the comparison is not valid. So, what you should do is you should ensure that the steady state values are same while you are trying to approximate the system. So, how can I make the steady state value same? So, this is how you can do that. Since you are going to approximate this, take this 10 out from here. Okay. Do not change the dominant poles, the dominant pole should not be changed, the dominant poles remains the same. Okay. Now, this becomes 2 by S by 10 plus 1, S square plus 2S plus 2. Okay. Now, get rid of this. Okay. So, now your approximated system is this. Okay. Now, you see the steady state value of this also is 1, for this also is 1. So, let us try to see what will be the effect of that. So, let me just write GAPPX final. So, this is our final thing, right. So, 2 by S square plus 2 into S plus 2. Okay. So, let me just remove the figures, previous figures, okay, and let us try to do the same thing again. So, step G, this is the original system, hold on, and then step APPX final. So, let us see, both the responses are almost similar, at least at the steady when t is increasing, and the transient part there will be effect, but when it comes to the steady state part, this is okay. So, this is how you can approximate second order systems or higher order systems with second order system. For the 0 case also you have to do the same thing, you should maintain that the final values are same. Okay. Now, this how does this help us? It will help. Now, see, now I can go ahead and model a system, find out the closed loop transfer function and check whether something is dominant or not. If there are 2 poles which are dominant, you ensure that those are the dominant poles, you check to other poles or 0. If the poles are 10 times away or the zeros are 5 times away from these dominant poles, you can approximate the system with second order systems. Okay. So, now we do not have to study till all the different types of orders of a system. We do not have to go for third order, fourth order, we do not have to study all that, because we know a way of, we know when can a higher order system be approximated by second order system. If it cannot be done, then also what can be done? We will talk about that during controller design, but remember that this is what we can do. So, and one more thing that you have to remember is that when the formulas that we have got for specifications, you can only apply them for second order system, they are not valid for higher order systems. Only when we approximate the higher order system with second order systems, we can apply those, and then since we have approximated already, so we can go ahead and find out, we can use those formulas to find out the controllers for the system. It might not be always possible to do that, but in many of the cases it is possible. We will stop here today and then next look into another specification in the next class. Thank you.